We talked about fission, breaking apart nuclei. The opposite, the sort of converse nuclear process is then fusion, where you're fusing things together. You're actually combining nuclei to create larger nuclei. The names, I don't know, I tend to get it mixed up, right? But fusion at least makes sense, the name-wise. You're fusing things together. And I usually just think fission is the other one, breaking things apart. So we have a diagram of an example of a fusion process. This is fusing hydrogen-2, a proton and a neutron nuclei, and hydrogen-3, proton and 2 neutrons. So that fusion process ends up producing helium-4, the standard helium, 2 protons, 2 neutrons, and some energy comes out with that, along with a separate neutron with that energy. So this example, or this diagram, is actually part of the process of how the sun produces energy. It fuses hydrogen to make helium. So in the sun and in stars in general, they're just big balls of gas. The initial phase is hydrogen, so it's a big ball of hydrogen basically, and it's pulled together under the force of gravity. So all the hydrogen attracting each other, you get enough of it together, it starts to pull together to form this sort of sphere, and the gravitational pressure, or the force of gravity from all that hydrogen, starts to crush like the core of that star to incredible pressures and temperatures, enough that you end up getting to the point where you can fuse nuclei together. And once that process starts, you sort of ignite the fusion core of a star, then that is producing energy, and it's also producing a pressure that ends up pushing back up against gravity, the gravitational attraction of all this stuff. And you end up with this sort of picture where gravity is starting to force the star together to collapse. Fusion is pushing things outward, and you get this balance where you get a stable star that lasts for billions of years. I'm pretty sure this state is called hydrostatic equilibrium. Not that you need to know that, which is interesting. So a little bit more detail about the fusion process that goes on within our sun, and within the first kind of stage of the star's lifetime is this fusion of hydrogen nuclei, or hydrogen nuclei is just a proton. So it's a fusion of protons, fusing protons together. It's called the proton-proton chain. So we'll look at this process, but the net effect is that you release about 26 mega-electron volts for every full proton-proton chain. And so the pictures here are showing the same thing, just in kind of different forms. The one on the left is maybe a little bit more detailed, where you see the first fusion process that starts this chain is just 2 protons, 2 hydrogen nuclei. Fused together, you get hydrogen-2, proton and a neutron in one nuclei. Out of that, you also get, looks like a positron and a neutrino. So then you have that hydrogen-2, that deuteron, and if that gets smashed into by another hydrogen nucleus, another proton, then we get fusion again and form helium-3. So 2 protons and 1 neutron. And there's many of these things happening in the sun all at once, and so you end up with a bunch of helium-3 flying around, and if those two smash into each other hard enough, then you get this last line where you fuse 2 helium-3 nuclei in order to form helium-4. That's the stable helium. Along with that, you end up getting back out 2 more hydrogen nuclei, 2 more protons, a positron and an electron, which tend to find each other and annihilate. It's a process we'll probably talk about more in the next chapter. But matter and antimatter together, they tend to destroy each other and release gamma rays. And this is just, again, another way of showing that picture, right? Maybe a little bit more pictorially, where you have these sort of 2 processes going on, where hydrogens fusing together to form deuterons. Each of those gets hit by another hydrogen to form that helium-3. Then the 2 helium-3s need to find each other to form helium-4. So this is sort of the overall picture of this whole chain, right? Start and end. So let's look at example 10.11, which puts together a good amount of stuff that we've talked about already. And yeah, it's a nice example. If we know that the power output of the sun is roughly 3.8 times 10 to the 26 joules per second, or watts, and most of this energy is produced in the sun's core by the proton-proton chain you're just talking about. This energy is transmitted outward by the process of convection and radiation. We don't really have to worry so much about how it gets to us, right? But most of this energy we're saying is produced by that proton-proton chain. So if that's the case, how many fusion reactions per second must occur to supply this power radiated by the sun? And then what is the rate at which the mass of the sun is decreasing? And lastly, in 5 billion years or so that the sun's been around, how much of that hydrogen will have been depleted? And what is the percentage of the mass lost by the sun due to this process? So in part A, we're asked how many fusion reactions are happening per second to make this energy. And it's a little bit of a handmade thing because there's actually multiple fusion reactions happening within the PP chain, that proton-proton chain. Right? There's like 3 or 4 different steps. We're just going to treat it all as sort of that overarching picture where you start with the 4 hydrogens, you end up with the helium nuclei and other things. Just treat that as like that's one fusion reaction here. That'll simplify our work here in part A. If we do that, then we're starting out with 4 hydrogen nuclei. We're ending with 1 helium one, 2 positrons, 2 gamma rays, and 2 neutrinos. So I already kind of told you about the energy released per this reaction overall. It's about 26, but we're going to use this as an example to find that energy based on the mass defect again. And to do that, we need to know what the change in mass is. And then whatever that change in mass is between the 4 hydrogen and then the helium and this other stuff, that's the energy that's released, and we can get that energy by multiplying by c squared. Looking at this process, we're starting with those 4 nuclei, so 4 times, I'm going to write it in atomic mass units. I'm not sure if we've written down atomic mass of hydrogen, or the atomic mass units of hydrogen, but that's what it is. And then we need to subtract the results. Okay? I'm going to subtract the mass of a helium nuclei, 1 helium nuclei, which is 4.0002603 atomic mass units, plus the mass of these other things. And look over here, gamma ray, right, this is a photon, doesn't have any mass, we need to include that. They do technically have some mass. That's a current topic of experimentation now. What is the mass of these neutrinos, right? But it's very small. It's so small we don't really need to include it in this calculation. So really the only other mass is these positrons. So plus 2 of them. In terms of atomic mass units, it's 0.000549 atomic mass units. This was the helium, these are the positrons. If you just put all that stuff together, we're going to get 0.0276 atomic mass units. That's the mass defect, so that energy that's released is that defect times c squared. We can essentially just convert the atomic mass unit to mega electron volts per c squared. So to do that, this is our mass defect, and the conversion between mega electron volts is basically the mass of 1/12 of a carbon-12 nuclei in terms of mega electron volts per c squared over U. And we're running out of room here, but this was just the mass defect conversion. We're going to multiply by c squared. In the end, we're going to get 25.7 mega electron volts, right? And that's per reaction. So for each one of these full proton-proton chains, we get 25.7 mega electron volts, which is very close to what I told you. I told you it was about 26. Oh wait, that's not all of part A, right? So that's the energy released in each reaction. If we want the total energy released per second to be that 3.8 times 10 to the 26th, then we just need to divide that total energy release per second by the energy release per reaction. Just go ahead and do the conversion between joules and mega electron volts, and don't really need to show that. Hopefully we're alright with that. But that energy release per second in mega electron volts is 2.38 times 10 to the 39th mega electron volts per second. So divide that by the energy release per reaction. Comes out to be 9.26 times 10 to the 37th, and that's now reactions per second. Right? A lot of reactions happening per second in the sun. Alright, so that's A. Let's move that somewhere and look at B. B, what is the rate at which the mass of the sun decreases? Well, I think maybe we're going to talk about that in terms of kilograms. So in B, each reaction reduces the mass by this many atomic mass units, and we can convert that to kilograms by using that conversion factor from earlier. 7, and that is kilograms per atomic mass unit. Turns out that that is 4.58 times 10 to the minus 29th kilograms. That's in one reaction. So how many reactions were happening per second times that is going to tell us how many kilograms are being lost per second, or being reduced. So we're pretty much just going to multiply this by the reactions per second. Which is going to tell us that 4.24 times 10 to the 9th kilograms per second are being reduced. So that's the mass reducing per second in the sun due to these reactions in the proton-proton chain. Seems like a lot, right? That looks like a lot. But the sun is very, very big. Yep. So how does this sort of relate to the sun's mass overall? Particularly we're asked in the life cycle of the sun that this proton-proton chain happens is about 5 billion years. So in that time, how much mass is lost? So 5 billion years, 5 times 10 to the 9th, or 5 giga-years. Well, you don't need to do this, but nice just practice of unit conversion from years to seconds, minutes, hour, and one more 60 seconds per 1 minute. That all tells me that 5 billion years is 1.6 times 10 to the 17th seconds. So that's how long 5 billion years is. This is how many kilograms are lost per second. So multiply those two together. That tells me that the change in the mass of the sun over 5 billion years is 6.8 times 10 to the 26th kilograms. Again, seems like a lot. It is a lot of mass. But the mass of the sun itself is about 2 times 10 to the 30th kilograms. So the change in its mass overall, that relative to the full size of the sun, 6.8 times 10 to the 22nd over 2 times 10 to the 30th, so both kilograms, end up with 0.00034 or 0.034%. Right? So even though it's a ton of mass that's being lost over that 5 billion year period, it's really not that much of the sun's mass overall. We may get a little bit more into this in cosmology in the next chapter, but it's already talking about fusion and stellar evolution in a way. I would bring this topic up where the lifetimes of stars go through the process of burning hydrogen, and then later on maybe burning helium, and that's been through fusion. And you just kind of keep going up, and larger elements being fused together as the star ages and goes through these different processes. But thinking back to that binding energy per nucleon, the stars will go through processes where they get to larger and larger nuclei, fusing larger and larger nuclei. But it turns out once you get to iron, once you start producing iron in the core of a star, if you try to fuse more nucleons together, it ends up taking energy to do that. Instead of releasing energy, you end up kind of needing energy or intaking energy to do that. So beyond fusing iron, the fusion process ends up being endothermic, means it absorbs energy, which means it's energetically not preferable, meaning that iron ends up being the last element you sort of end up with in the core of the largest stars. But whether you get to that end or whether it ends sooner depends on the mass of the star. And in between, if a star is not massive enough, you might end up going supernova before that, where essentially the star finishes one of its fusion sort of cycles. So it kind of cools down in the core a little bit, and gravity ends up taking over again and starting to crush the star down again. And if it doesn't get hot enough to ignite the next stage of fusion, then gravity just keeps going down and crushing it down, and then you end up with this kind of ripple or reverse back that just blows the outer part of the star off of the star itself. So that forms what we call planetary nebula, where these pictures, the central kind of star there is the star that formed this planetary nebula, and the gas that you see around it is the outer shell sort of the star that's getting blown off. And besides just the outer shell of the star, when you have these events, these sort of explosions of stars in a sense, we call supernova, for a short period you get incredible energies in there. That's where you can form even larger nuclei. So even though it's not energetically favorable to do it inside of a star, when you have this explosion happening, there's so much energy around that you can form larger nuclei. You can fuse larger nuclei up to like uranium. You might have heard the quote from Carl Sagan that says something like, "We are star stuff." And that is to say that the elements, the things we're made up of, were fused inside of stars or created during explosions of stars. So this process of stellar evolution of blowing off part of its outer shell and creating larger elements is part of what seeds the universe with those larger elements and allows more complex things to form. We talked about nuclear reactors earlier, and those were using fission, breaking nuclei apart and releasing energy that way, and then converting that energy to electrical energy. It turns out that fusion is an even more efficient way of producing energy, or it can be. It produces more energy in general than a fission process will. So there is tons of activity, tons of experimentation, research going on to try to perfect, in a way, fusion in a reactor. So terrestrial fusion on the planet that we can actually use then to convert to electrical energy. It's a very difficult thing to do, partly because in order to fuse hydrogen, the temperatures you need to get to are like 10 million Kelvin. So it's very difficult to achieve this. That's not to say we haven't. We have created fusion. There are fusion reactors. They're just not efficient reactors right now for the most part, where you don't get more energy out than it takes to start and sustain that reaction. Still working on that part, but people seem to think we'll get there eventually. The image here is of one kind of fusion reactor, which is called a tokamak. And it's basically like a donut-shaped vessel, and all the stuff inside, a lot of that are magnets or electromagnets, because you sort of put hydrogen into this vessel and then start dumping energy into it one way or another, and in order to keep that hydrogen from just destroying the vessel itself, you tend to use magnetic fields in order to keep the hydrogen in this area that's sort of away from any walls or any outside of the vessel. Okay, so getting back maybe to thinking about what happens to the stuff that comes out of nuclear processes, and particularly in terms of what that stuff can do to biological material, what it can do to you, what it can do to animals and plants, all that different stuff. So one thing that can happen is that radiation, so like those gamma rays, alpha rays, beta rays, they can actually alter the structure of DNA and can affect the ability of DNA to repair itself. And there's a number of things that can happen as a result of that. Your cells can start to sort of become dormant, not reproducing and not dividing. They can, in a way, commit suicide, called programmed cell death. And it could also even just lead to the cells just dividing themselves in an unregulated way, just sort of proliferating. And that's how you get tumors and cancers, or one way to get cancers at least. So if we're going to quantify radiation, and particularly like organic material or a biological organism absorbing radiation, we're going to quantify that. The base unit is a rad, radiation dose unit. So 1 rad is 0.01 joule per kilogram. Right? So this is a energy that's being deposited in tissue, in organic tissue. So a rad is sort of a base unit, but it turns out that the different kinds of radiation, right, the alpha rays, the gamma rays, the beta rays, they affect organic tissue differently. Some of them are just more harmful than others. So a rad tells you how much energy is being deposited in tissue, but that doesn't necessarily tell you how damaging that radiation is. It doesn't necessarily give you a good measure of how damaging it is. We also have this thing called relative biological effectiveness, RBE, which quantifies the relative damage that different kinds of radiation can do. So an X-ray, for instance, is 1 on the effectiveness scale. Effectiveness is a weird word, it's like damaging scale. So X-rays and gamma rays, pretty similar. Beta rays that are fairly large energy, also about 1. Beta rays that are less energy is actually greater, 1.7. And I don't think I have this in a slide particularly, but the book talks about this, why a sort of slower form of the same kind of radiation might do more damage. And it's really comes down to the fact that the slower beta ray, or the beta rays are electrons, there's electrons zooming through things. So if an electron is actually slower, it can do more damage because it spends more time in material, versus a faster one which will shoot through real quick. And then also for neutrons, so this is not like alpha, gamma, or beta rays, it's just free neutrons. Well, free neutrons can come out of like fission, right? So it would be radioactive products. Protons also, and then alpha rays, and then actually just heavier ions, free nuclei, sort of the cells that fly around. So then we can make maybe a more useful quantitative measure of radiation, or the potential damage from the dose of radiation, by combining these 2 units, right? The energy deposited per kilogram, along with the relative damage that can be done by each kind of radiation. So those 2 multiplied together gives us a REM, Roentgen equivalent man. It's a weird term. But REM is just the rads multiplied by RBE. And then finally, Savart, SV, is just a scaled unit of REM. It's 100 REMs. Savart ends up being the sort of standard unit for dosage of radiation. And this gives you an idea of the sort of scale of the Savart and how damaging it can be. Anywhere from 0 to a tenth being no noticeable effect. I guess it should be said that these doses are saying that you're getting a dose over your whole body and it essentially happens all at once. That can be different than getting a dose in like a particular region. All that dose, say, goes to like your liver or something, or goes to your eyeball. Right? That can change how damaging it will be. Also, if it's not all at once, if you get this amount of radiation over an hour, a day, a month, then that's going to be less damaging overall. So it just gets increasingly worse and worse. About 1 Savart dose, you possibly can get fatal side effects. 2 to 5, 6, right? But if you get anywhere more than 20, your nervous system is going to collapse within a few hours. Yeah, so radiation, no joke. You know? However, that's not to say that we can't handle some amount of radiation, right? There's levels that we handle all the time. In fact, there's plenty of natural radiation that occurs just all around us. As I said a while ago, the Earth has a bunch of radioactivity happening inside that's keeping it warm. Right? Some of that stuff ends up going through us. So we get dose of radiation that way, we get dose of radiation coming down from the atmosphere. So these are some of the places where we get radiation from, and in terms of different locations in the Earth. And this is by millisivart per year. just from cosmic rays, from stuff hitting the upper atmosphere and that causing some nuclear processes. We get some radiation from that, from the decay of potassium, carbon-14, radon, and then also from medical devices, medical procedures. Yeah, because it turns out that we found out how to utilize radiation for medical applications, among other things, but they can be very useful in mapping the interior of the body without actually having to open it up. The whole process, I think, is fairly complicated, but the simple version of how we end up with images like this is you use a particular radioactive material and get it into the body somehow, either ingesting, injecting, one way or another, and that material, you create it or use particular ones in such a way that they'll accumulate in the areas of the body that you want to map. So once you have that radioactive material in the area of the body that you want to map, then you need to detect the radiation that's being released from those radioactive decays, or whatever radioactive process it is. So you have some sort of device that can actually detect, say, like the gamma rays that are being produced by decays of the material you introduced into the body. You have these detectors that see these gamma rays coming out of particular areas, and you can trace those gamma rays back to where the decays happen. Right? And so you end up sort of being able to pinpoint where all these decays are happening. And if you have enough of those gamma rays, you can really draw a nice map or 2D or even 3D picture of that part of the body. So on the left is of a brain, the right is an intestine. I'm not sure what that is. I'm not a doctor, that's for sure. But this one particularly uses what's called a PET scan, or a positron emission tomography. I think actually look at more in the next slide. But yeah, you can get these very interesting and useful pictures of the interior of the body via radioactivity. And the name for those isotopes that you introduce in the body in order to do this is radiopharmaceuticals. I think that's how you say that, radiopharmaceuticals. On the left there is a picture of one of these kind of scanners, SPECT, some kind of CT scanner. Yeah, I don't know very well the specifics of some of these machines. This one though, we have a diagram of that PET scan. In the PET scan particularly, you use a material that goes through beta decay, and particularly beta plus decay, so you end up with a positron out of the decay, and that positron very quickly is going to run into an electron. And again, when you have matter and antimatter, of electron and anti-electron meet, then they, what's called, annihilate, and you get gamma rays out. For this particular annihilation of a positron and electron, you get 2 gamma rays out of a very particular energy. It's like half a mega electron volt, and then shoot out back to back. So if you have this detector that can detect these gamma rays very nicely, you can point back to where that decay happened. If you have a number of these decays, then you start to kind of build up a picture of the topography or the 3-dimensional image. So these radiopharmaceuticals can be very useful things. And here we're seeing a chart of some isotopes that are used in the places that they're used as radiopharmaceuticals. So like in brain scan, you might use oxygen-15, or you might remember, I pointed out a while ago, this technium, I don't remember the exact name, TC, and 99M. So remember, M is indicating this is a metastable state of that technium nucleus. Just like an excited atom, like an excited hydrogen atom, this is a nucleus that's in an excited state, and it will decay, emit a gamma ray. You use that as a radiopharmaceutical. And in fact, that one is used in a number of different places. It's widely used, apparently, in this process. And then finally here, we talked about X-rays a couple of chapters ago, I think, because X-rays are created by electron energy transitions, usually between high energy levels and much lower energy levels, right? But if you get that large drop in energy of the electron, then you get that X-rays out. But X-rays can also give radiation doses, and so these are quantitative amounts for different kinds of X-rays, and that's in millisieverts. Millisieverts, remember, that's 1,000th of a sievert, and in that table earlier, it had to be greater than like 1/10 of a sievert to even start to really do anything. So these are all pretty low doses. It can be affected by the amount of time that it takes to get this dose, but in general, these are fairly low doses. All right, that is chapter 10, nuclear physics. So, oh my gosh, we're almost done. Chapter 11 is particle physics and cosmology. So I will see you then. Have a good one.